Hello and welcome to Call of Chemistry. This will be the fourth video regarding organic chemistry, some basic principle and techniques chapter of class 11. In this video, we will discuss about resonance or mesomeric effect. So before knowing about resonance, we have to understand why this resonance concept is needed and why it is so important. We will understand by two examples. First is carbon dioxide. The structural formula of carbon dioxide molecule is, and the standard C double bond O bond length is 122 picometer. But experimentally it is found that C double bond O bond length in CO2 is 115 picometer. And the second example is benzene. Standard C double bond C bond length is 1.34 angstrom and standard C single bond C bond length is 1.54 angstrom. But all the CC bond present in benzene are identical. That is, all the CC bond in benzene are identical with bond length 1.39 angstrom. So how can we explain this phenomena? Now there comes the resonance concept to explain all these properties. So in carbon dioxide, if we draw the structure, here is one lone pair, here is another, here also these two lone pair. According to the resonance concept, this lone pair goes over here and this move to there. So we get here is positive and here is negative. So why there is positive? Because atomic oxygen has 6 valence electron, but here it is 1, 2, 3, 4 and 5. So 1 electron short from the atomic oxygen. So that's why the positive charge is here. And why it is negative charge? The atomic oxygen has 6 valence electron and here it is 1, 2, 3, 4, 5, 6 and 7. And that's why this oxygen has the negative charge upon resonance. This also has another possible canonical structure, that is, so it is termed as one canonical structure, it is 2 and it is 3. Therefore, carbon dioxide cannot be represented by any of the contributing structures. Carbon dioxide is nothing but the average of all these canonical forms. And upon resonance, we can see that this double bond is no longer a double bond. It converted it into a triple bond. That's why the C double bond of bond length changes to 115 picometer. Similarly, for benzene, if we draw the canonical structures of benzene, this will be here, and the resonance hybrid is represented as, this is the resonance hybrid of benzene. So you can see that this single bond upon resonance turns to a double bond. Therefore, all the CC bonds in benzene are in between single and double bond character. That's why we see the all CC bond in benzene are identical with bond length 1.39 angstrom. So resonance concept is able to explain all these properties. Now, in which systems resonance takes place? If one system contains pi sigma pi conjugation, or one system contains n sigma pi conjugation, or if a system possesses vacant orbital sigma pi type conjugation, or if vacant orbital sigma n type conjugation is present, and if radical is present, then sigma pi type conjugation, then there also be resonance take place. Firstly, there is pi sigma pi conjugation. Suppose this system is taken. This is 1, 2, 3, 4, and it is buta 1, 3 diene. Here we can see that this is a pi bond, this is a sigma bond, and there is a pi bond. So this is an example of pi sigma pi conjugation. Now how resonance takes place? Simply this pi bond shifts over here and this pi bond moves over here, and we get the canonical form, that is, we know that atomic carbon contains 4 valence electrons. So here it is 1, it is 2, 3 and 4 valence electrons, and after resonance this carbon contains 1, 2 and 3 valence electrons. So 1 electron short from the atomic carbon, so that's why it contains positive charge over here. And this carbon primarily contains 1, 2, 3, 4 valence electrons, and this pi bonded 2 electrons shifts over here. So this is another 2 electrons. So 1, 2, 3, 4 and 5 electrons. So 1 electron extra is present than that of atomic carbon. So there is a negative charge over here. Now if we draw the resonance hybrid of buta 1,3 diene, it will be this is canonical structure 1 and this is canonical structure 2. Now between 1 and 2, which one is more stable and which one contributes more to the resonance hybrid? Now between 1 and 2, 1 is more stable as it contains maximum number of covalent bonds. So here you can see that here is 1, 2, 3, 4, 5, 6, 7, 8 and 9. So here 9 covalent bonds is there. But here 1, 2, 3, 4, 5, 6, 7, 8. So here it is 8 covalent bond is present. Again, this 2 canonical structure has a charge separation, that is, here is positive and here is negative. So this contains a charge separation which is unstable. So this one canonical structure is more stable and it contributes more to the resonance hybrid. Next is the n sigma pi type conjugation. What does this n denote? N denotes non-bonding electron pair or lone pairs. Suppose we take this system, and here we can see that there is 1, 2 and 3 pairs of non-bonding electron in chlorine. This is n and then it is sigma, then it is pi. So this is an example of a system that possesses n sigma pi conjugation. How resonance can take place? Simply, this non-bonding electron pair shifts over here and this pi electron shifts over here, and we can draw the resonating structure, that is double bond CH negative. Now, how positive charge is there in chlorine and negative charge is there in carbon? We know that atomic chlorine has 7 valence electrons, that is 1 2 3 4 5 6 and 7. So 7 valence electron is there. Upon resonance, this chlorine has 1 2 3 4 5 6 valence electrons. So 1 electron short than the atomic chlorine. That's why a positive charge is there on chlorine. But we know that atomic carbon has 4 valence electrons, that is 1 2 3 and 4. But upon resonance, this carbon contains 1 2 3 and an additional electron pair, which is these 5 electrons. So that is 1 2 3 4 5. So 5 electrons are there. 1 electron extra is present than the atomic carbon. That's why this negative charge is there. So this is one canonical structure and that is two canonical structure. Now between 1 and 2, which one is more stable and which contributes more towards the resonance hybrid? And if we draw the resonance hybrid, that is here it is. Delta positive and it is delta negative. Now between 1 and 2, 1 is more stable, because in 2 we can see that as chlorine is more electronegative, so positive charge on chlorine is less stable. That's why 1 is more stable and it contributes more towards the resonance hybrid. Next type of conjugation is vacant orbital sigma pi conjugation. Suppose this system is taken. Now how it is generated? This is generated from suppose L is a leaving group and L should be iodine or bromine or chlorine etc, and it is a leaving group. So if L group leaves via heterolytic cleavage, then this carbon will possess a positive charge. Now this is the vacant orbital and then it is sigma, then it is pi. So this is an example of vacant orbital sigma pi type conjugation. Now how resonance can take place in this system? Simply this pi electron moves over here and we get the resonating structure. So here you can see that this carbon contains 3 valence electron, that's why it contains a positive charge. And if it is one canonical structure and it is two canonical structure, and the resonance hybrid will be such like that. This is the resonance hybrid. So you can see that 1 and 2 both are identical and have same stability, and both contribute towards the resonance hybrid. Now the next type of conjugation is vacant orbital sigma n type conjugation. Suppose this system is taken. So this is the vacant orbital and this is sigma and this is n, that is non-bonding electron pair. So here vacant orbital sigma n type conjugation is present. Then upon resonance, this electron pair moves over here and we get the canonical structure double bond O positive and CH3. So we know that atomic oxygen has 6 valence electron is 1, 2, 3, 4, 5 and 6. But upon resonance we can see that there is 1, 2, 3, 4, 5 electrons. So 1 electron short from the atomic oxygen. That's why this oxygen bears a positive charge. This is one canonical structure and this is two canonical structure. If we take another example, that is, so here it is vacant orbital and then it is sigma, then it is non-bonding electron pair. So here also vacant orbital sigma n type conjugation is present and this electron pair moves over here and we get the resonating structure such like that. And we know that atomic nitrogen has 5 valence electrons, that is 1, 2, 3 and another 2 electrons for these 2 methyl. But upon resonance this nitrogen has 1, 2, 3 and 4 electrons. So 1 electron short from the atomic nitrogen, that's why this positive charge is here. One canonical structure and it is two canonical structure. Now between 1 and 2, which one is more stable and contributes more towards resonance hybrid? You will tell that in 2, positive charge resides on more electronegative nitrogen atom. So 2 will be less stable. But in this case, octet fulfillment is given greater priority. We can see that in 2, both this carbon and nitrogen is fulfills octet configuration because this is 1, 2, 3, 4, 5, 6, 7, 8. So nitrogen's octet is filled up. Then this carbon also you can check these 2 carbons has octet configuration. But in one canonical structure, this carbon does not fulfill the octet because this is 1, this is 2, this is 3, this is 4 and for this hydrogen another 2. So total 1, 2, 3, 4, 5, 6. So this carbon contains 6 electrons. But both these carbon and nitrogen contains octet fulfillment. That's why canonical structure 2 is more stable and contributes more towards the resonance hybrid. Then the next type of conjugation is radical sigma pi conjugation. Suppose this system is taken. So how it is generated? This comes from, suppose there is a leaving group here, then homolytic fissions occur. Then this radical is generated on this carbon and a chlorine radical is generated. Now how resonance will take place in this compound? Simply homolytic fission takes place and we get radical over here and radical over here. Now these two radical combines and we get a pi bond. So simply we can write that this radical is known as allyl radical. Now we move on to the next topic, that is how to calculate bond order in molecules showing resonance. The formula is bond order total number of bonds between two atoms upon total number of canonical structures. We'll understand by an example. We'll take carbonate as an example. If we draw the canonical structure of carbonate, so this moves over here and this moves over here, and we get again this moves over here, this moves over here, and we get. So if we calculate the bond order, we can see from the formula that is total number of bonds between two atoms upon total number of canonical structures. So if we consider this bond, here it is 1, here it is 2, and here also it is 1. So bond order will be 1 plus 2 plus 1 upon, there is 3 canonical structures. So here it is 3. So 4 upon 3, that is 1.33. So we here consider that this bond. So here is 1 bond, here it is 2 bonds, and here also it is 1 bond. So 1 plus 2 plus 1 upon 3. So it is 1.33. That is how we calculate the bond orders. Now we move on to the next topic, that is resonance effect or mesomeric effect. Resonance effect is classified in following types, that is plus R or plus M effect and minus R or minus M effect. Firstly, we will discuss plus R effect. If a conjugated system has an electron donating group, then it is said to have plus R or plus M effect, such as if OH group is there, or SH or NH2 or NHR, where R is an alkyl group, etc. These all are electron donating groups. If it present in a system, then it will show plus R effect. If we will take an example, suppose we take aniline. So this lone pair upon resonance moves over here and this pi bond moves over here, and we can draw the canonical structure. A negative charge is here and two double bonds, and it is positive charge. Then it moves over here, it such a way. Then it is similarly it moves over here and it there. Then it moves over here and we get this canonical structure. So here you can see that this NH2 group pushes its electron pair towards the system. So that's why it shows plus R effect. Now we'll discuss about minus R or minus M effect. If a conjugated system has electron withdrawing group in it, then it is said to have minus R or minus M effect. Suppose we take an example of electron withdrawing group, that is NO2 group, and we take the example of nitrobenzene. So if we draw the canonical structure, then this pi electrons moves over here and it moves over here, and we get this resonating structure. So it is positive charge, then it moves over here, and it is. So you can see that this nitro group pushes the electron towards itself. So it is actually deactivating this phenyl group. So this shows minus R or minus N effect. So by this I am stopping here. If you have any doubt, please let me know in the comment section. Please like, share and subscribe my channel. Thank you.